Hello, good morning, and welcome back. So today, in Mathematical Foundation of Robotics, we are going to discuss about representing orientation using Euler angle. Okay, just we can recapitulate and we can give you some example problem. Last day, we explained how to describe a composite rotation matrix when you are rotating any rigid body about any arbitrary axis. Okay, so maybe you can take an example. Find out the composite rotation matrix that represents rotation of, say, anything, any 45-degree angle about an arbitrary axis R, say, which is equals to 2, 2, 2. Okay. So this is directly you already know the formula of composite rotation matrix. The basic idea was very clearly to be understood, right? So when you have an object, the way we deduce the composite rotation matrix was that this, with respect to any coordinate frame, orthogonal coordinate frame, this R was given, and without loss of generality, we assume that R is a unit vector which has a component of Rx, Ry, Rz. Okay, Rx, Ry, Rz about three orthogonal coordinate frame x, y, z. Okay, then to get this actually this angle, what we did, we projected this vector, say OR, on xy plane. Okay, and then we rotated about this axis so that projection of OR will be coinciding with any of the principal axis. It could be Z, it could be X, it could be Y, and then you get the operation, and once the operation is over, then you will have to come back to this orientation by giving the reverse rotation uh, about the principal axis. So that was the fundamental thing, okay, which gave you the composite rotation matrix um, uh, description. Okay, so once you have done that, then you can just you see r is given and theta is also given, and in terms of this r, okay, and theta, your composite rotation matrix can be calculated, and that's very simple but elegant way of describing by matrix method orientation of any rigid body when it is rotated not about any of the principal axis but any arbitrary axis, known axis. Okay, so that's very important many times, and we also, once we got the composite rotation matrix, we can figure out, if composite rotation matrix is given, we can figure out from the same inverse procedure, we can figure out what is the R. Okay, so either way, if the orientation is given, composite orientation matrix is given, I can figure out also the 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 arbitrary axis about which the rotation might have been taking place. Now, having said that, we also would like to describe orientation using Euler angle. Euler, is a great mathematician. He seeing the orientation description is a little bit problematic. He devised a methodology which can make your life easy in terms of figuring out the um, angles, which is known as Euler's angle, okay, of orientation, given the orientation matrix. Because the issue is here, you see, you have the rotation matrix, which is of this nature, right? R21, R22, R23, R31, R32, R33. So if somebody is giving you, it's very tricky to figure out what combination of rotation along about principal axis has generated this, because there is no unique way, or what this arbitrary axis principle also helps you, that what is the arbitrary axis about which the body has been rotated. Um, Actually getting phi, theta, psi, where phi is the angle of rotation about x-axis, y is the angle of rotation about y-axis, psi is the angle of rotation about z-axis. Given these 9 elements, because this is 3 cross 3, and we have 3 degrees of freedom, phi, theta, and psi. So given this, figuring out this is tricky, okay? Given, and you are trying to figure out. So exactly, we are trying to take the help of Euler representation to figure out this phi, theta, and psi from this. And for that, there are some standard Euler representation of orientation, and that's very important. Why important? You see, say this is my aircraft, okay, and I have told you in my earlier classes that there are when it is flying in the air, it has at a particular position, okay, it has 3 degrees of orientation, right? Which is can be described as this is actually about this. This is called yaw, okay. This is yaw, and this is roll, and this is pitch, okay. So these 3 angles are to be locked with the orientation. And you see, this is a, say, runway. It has a particular orientation, the fixed, okay. So when it is trying to land, it must lock, means it must orient itself with this runway perfectly. And to make it happen, the controller must know, for landing in this particular orientation, what are the angles are to be controlled by how much amount, okay. And that is the major issue, which and not only in aircraft, and for example, same thing I will give an example in robotics. The robot gripper, for holding an object, robot gripper has to orient itself. So you see, robot gripper also has yaw, has roll, and pitch, okay. So robot gripper also need to orient its gripper, and the principle is same actually, as you are seeing here. And not only these 2 practical example, if you try to design game, okay, where you will have to manipulate the orientation, okay, for designing some game. It will just move around position, it will change position and orientation. Position change is not problematic, as you know, but orientation change is problematic because it is non-unique, okay. So that's why all the story we are telling you, that Euler angle can help you in figuring out the orientation, that figuring out theta, phi, and psi for a given orientation, okay. So there are 3 types of actually Euler angle. There are 3 types of Euler angle representation of orientation. What are those? You see, I have uh, this is psi about z axis. Okay, this is your z, say psi about z axis, about this is if it is O. Okay, so about OX, this is phi, about OY, theta, about OZ, psi. So these are the three angle of orientation which can describe the orientation of the aircraft or the gripper or runway or anything, right? So now we need to find out. So there are, I will tell you the three types of oil and anchor representation, and these three type can also give birth to many other. For example, in Craig, they have discussed about many more oil and angle representation, but they are equivalent, which you will understand, right? So three types of oil and angle. Normally, those oil and angle operations are giving about any of the principal axis, but we can actually take three types which are equivalent to describing the gyroscope. You know, gyroscope is actually any rotating object can be a gyroscope, can be considered as a gyroscope. The aircraft is a gyroscope. Yes, it has rotation axis. Say, okay, I describe I describe any of the axis rotation. Then we can call spin axis, precision axis, and torque axis. Say, if I provide torque about roll, okay, so aircraft will try to precess. Okay, that's a fundamental gyroscopic principle we will discuss some other time. But gyro orientation can be described by these three common types of Euler's orientation representation. Okay, types of Euler angle. Okay, so type 1, type 2, type 3. Okay, say, and what are the sequence of motion? Sequence of rotations. One is phi about, say, OZ axis, theta about OU axis, psi about OW axis. So these are the rotations can be described a gyroscope's orientation or this aircraft's orientation using these three parameters. Also, it could be phi about OZ axis, then theta about OY axis, psi about OW axis. And there is another type, okay, about OX axis, phi theta about OY axis, and phi about OZ axis. Okay, so what is actually your psi is yaw, then phi is roll, and theta is pitch. So these are three standard Euler angle representation, and from here you can derive many more because, as you know, the rotation composite rotation matrix can be achieved by different sequence of rotations, which we discussed in my earlier lectures. Okay, so type 1 means roll, pitch, yaw. So this is roll, pitch, yaw. Okay, and this is your um, roll, pitch, this is roll, is roll, pitch, and yaw. This is your phi is roll, then theta is pitch, and then this is yaw, and this is also uh, yaw, pitch, roll, phi is roll. Okay. Uh, okay. So about y-axis, uh, y-axis is y-axis is pitch, right? So roll, pitch, yaw. This is roll, pitch, yaw. But you see the difference. The uh, the orientation, the operation has been given about different axes. So what will be the composite rotation matrix? Say for type 1, composite rotation matrix RC for type 1 Euler angle, what it will be. You see, I told you that you can just put it like this. This is 3 cross 3 unitary matrix. Now rotation has been given about OZ axis. So OZ, is it inertial frame principal axis or no? I will draw maybe. Okay, just so this is your, I am drawing as per this. Okay, Z orthogonal coordinate frame. Um, okay, okay, or I will draw in common sense. Okay, commonly that will be, actually I need a little bit more space here. Oops, sorry about that. This is X, this is Y, this is Z. Initially, I have written, that means the body coordinate frame are also aligned. Okay, and then what you have given, type 1 means you have given orientation about a rotation about OZ axis, okay, by an angle phi. So you are looking from here, say you are looking from here, phi is positive angle, and clockwise, counterclockwise, looking from here, this is positive phi. Okay, and you see the body coordinate frame, as a result of that, on xy plane it will flip. So new, this is say earlier u, this is a new position of the u, this is a new position of the v after giving this rotation, and they flipped in the xy axis, on the xy axis. Okay, and then what you have done, so this is figure which you have done, then you are giving an operation theta about OU axis. So this is your O, say OU axis. This is new OU axis, and you are looking from here. So counterclockwise, this is actually theta. Okay. So as a result of that, what will happen on YZ plane? YZ plane, you will have, and what was this angle? This angle was phi. Okay. So this angle was phi, and this angle will be theta, and this will also flip W. This is actually theta. Okay. Okay. So after giving this operation, your figure will be like this, and then you are rotating about OW axis by an angle psi. Where is OW axis? Here is OW axis. So you look from here. Okay. So it will be counterclockwise. Okay, by an angle psi. Okay. So perpendicular to OW axis, then this will actually flip V, and you see U. That's it. So after giving this roll pitch yaw, your body is undergoing so many deformation, and then I need to calculate, say, I need to calculate composite rotation matrix. So what it will be? So this R rotation about Z axis by an angle phi, it will be pre-multiplied, and then these operations are about the body coordinate frame. So where they will go, they will be post multiplied, and what will be the principal matrix? They will be remaining same, means x or u. So this is u by an amount theta. So this is number one operation, this is number two operation, and then R Z means W by an amount psi. So these are the composite rotation matrix RC. So this is equals to R Z phi, R U theta, R W psi. So, and you know what will be the composite rotation matrix? Say cos phi minus sin phi. Okay, because about Z by an amount phi. So you know already what they are: sin phi, cos phi, 0, 0, 0, 1. Okay, so this is your R Z phi. Already we taught in the first couple of classes. And then second matrix, principal matrix, about x, right? So it will be 1, 0, 0, then 0, 0, and then cos theta minus sin theta, and then sin theta, cos theta. So this is important to note that this theta are positive. We have shown all positive directions, so that if other things there negative clockwise, if clockwise, then you can just make it negative. Okay, and then cos psi minus sin psi 0, sin psi, cos psi 0. Okay, so this is your okay. So these are all known to you. So now you multiply these, then multiply with this, and you get So you see, I am showing you how to derive composite rotation matrix for type 1 Euler angle. Similarly, it will be an exercise to do the to deduce composite rotation matrix using same the post multiplication pre-multiplication principle. You see about which axis? Inertial frame? Yes. So they will be pre-multiplied. Inertial frame? Yes. Y-axis of the inertial frame pre-multiplied. This one about body frame, Z-axis of the body frame post-multiplied. This one again inertial frame, inertial coordinate frame, inertial coordinate frame. So your pitch roll are all the operations are giving about the principal axis of the inertial coordinate frame, and accordingly the composite rotation matrix will change for type 1, type 2, type 3 representation of orientation. Okay, we are showing you type 1 Euler angle representation, and if you just make the multiplication, what you will get is the following. If you do the multiplication, then RC will be, say, okay, so cos phi, then cos psi, then sin phi, cos psi, sin theta, sin psi. First column. Second column will be, first column, one minute, so I need more space. Okay, so I don't need this anymore. You already know. Minus sin phi, cos theta, sin psi, this plus cos phi, cos theta, sin psi. This is, so this is first, this is my first column. Second column is minus cos phi, sin psi, minus sin psi, cos theta, sin psi, cos psi, okay, minus sin phi, sin psi, plus cos phi, cos theta, cos psi, and then this is sin theta, cos psi. Okay, I need more space, so I will erase it. Okay, so this is my composite rotation matrix for type 1 Euler angle representation. So sin phi, sin theta, minus cos phi, sin theta, and this is cos theta. Okay, so this 3 cross 3 matrix actually is representing any rigid body's orientation following the description of type 1 Euler angle. But remember, type 2, type 3 Euler angle representation will have different composite rotation matrix. So as I told you that whatever is convenient for you, that type 3 very popular type we have given because they are related to gyroscopic motion, and gyroscopic motion can describe the orientation perfectly. So you can use any of them, or in other book if you see that all the rotations are giving along some of the principal axis, then also they are perfect. They are because here this is equivalent to, okay, so matrix will not change if I make this this thing, no, z psi, then followed by x theta, followed by z phi. So this is z x ZXZ, okay, ZXZ type Euler angle representation. Likewise, you could figure out what will be the equivalent angles if all the rotations are given about the about some of the principal axis of the inertial coordinate frame. So once you know the once you are knowing the principle, this is very easy, isn't it easy? So this is one representation, right? Now say this is equals to my 1 3 r 2 1 r 2 2 r 2 3 r 3 1 r 3 2 r 3 3. Now say this is the orientation of a required orientation of a robot gripper. Okay, so to achieve this, I need to calculate theta, phi, and psi, right? So theta, phi. I need to calculate. So I can use this. Okay, this is equals to this, and since this is given, all the elements are known. So in terms of 8 and 2 function, I can easily get theta, phi, and psi. That's it. Okay, so that's very convenient for a pilot to actually figure out once this is given. For example, Allahabad airport's orientation is given. Okay, suppose it is completely manually, pilot is operating, so his system will know that, okay, corresponding to this orientation, what will be the angles I need to lock or fix my aircraft. And we have not deduced that. Actually, theta will be in terms of 8 and 2 function. 8 and 2, some say R1, 1. This is hypothetical. I will deduce it. Okay, don't worry. Theta is this. Similarly, phi will be 8 and 2 in terms of these elements. Okay, some of these elements, say R2, 2. Because there will be square root of 1 plus square root, all kind of things will be there, which are very simple, and we will deduce it. Okay, just elimination. Okay, uh, nothing but elimination. So psi also will be 8 in terms of 8 and 2 function will be given. The moment these elements are known, all these angles will be known, and once it is known, the pilot will try to manipulate. Okay, so psi is about your angle, it will manipulate. Phi angle, it will manipulate. And psi angle, it will manipulate. You will see the aircraft is actually moving like this, and this is, it has locked with this runway, and then it will touch down. Okay, so no matter, okay, they have inertia, their navigation system, so you don't need to see this is plan based, so aircraft need not see the runway, all kind of things. So automatically this controls are available automatically. Aircraft can be controlled to land perfectly. And in case of robot, if I give some object on the table, and of the object of different size and shape. So for that, I need to say orient my gripper, robot gripper. So I can do that using same technology. Okay. So wonderful, right? So we had a rotation matrix having 9 elements, but we need to figure out that what they are translated in terms of theta, phi, and psi about 3 principal axes or body coordinate frame, whatever, right? 3 principal axes that we can derive using Euler's representation, which is very straightforward and easy. Now, every easy thing has some limitation, right? What is the limitation in case of Euler angle orientation? Great limitation. Huh? Okay, now suppose this is instead of a Boeing aircraft, passenger plane, instead of that, it is a fighter plane. Okay, and it is maneuvering, yaw, pitch, roll, and in such an certain orientation, suppose any of the 2 axes of rotation are coinciding. Okay, sometimes it need to maneuver like this, or it need to maneuver like So in those situations, when any two axes, we can call it gimbal axis. Okay, this is jargon term. Okay, these are called gimbal axis. So any of the two gimbal axes, when they coincide or become parallel, okay, in case of robot gripper, then what will happen? Then this 3 cross 3 matrix will not be of full rank, that you perhaps know in just a little bit linear algebra, but don't worry if you do not know. Okay, I'm going to tell you that when these two axes, out of three axes, two axes will coincide, then the 3 by 3 rotation matrix uh, will have either row or column dependent. Okay, so if determinant of this matrix will be 0. Okay, so this situation is very dangerous. Okay, because now this has lost 1 degrees of freedom. So the structure here taught as if has only 2 degrees of freedom to maneuver, and extremely difficult. That is called singular configuration. So you cannot figure out that because the moment this is actually 0, you cannot calculate its inversion, right? And that situation is called Gimbal Lock. So here we see, let us see, this is okay. Practically aircraft, I am taking the example. Robot or gripper orientation, I am taking example. How about game design? They are using the same kind of technology. You are designing a game, for example. Okay, a player is actually heading in a soccer game. You have some players, okay, digital, of course, and then you are trying to imitate the game, and it is heading some ball or kicking some ball. And if Gimbal Lock happens, then what catastrophic video or images can be generated. Let us see. And then I think Gimbal Lock will be completely understood. Now, Gimbal Lock in a technical term, when the rotation matrix loses, is not a full rank. Okay, it rank maybe say 2 instead of 3. When it will happen? When either of the 3 axes are actually coinciding, this will happen. Okay. So, for example, this is pitch, right? So this is the angle about which pitch. So pitch is so much. Say aircraft is vertical, then pitch and yaw axis, x-axis and z-axis becomes collinear. Okay, same, and then its determinant will be. Then we call that situation Gimbal Lock. Okay, and technically it loses its degrees of freedom, and determinant will be 0, and we called those orientation for which x and z or y and x or z and y are coinciding. They are called singular orientation of the robot, and those situations are called Gimbal Lock situation. So that's the fundamental problem. If the Gimbal Lock situation is there, then you cannot control the aircraft may crash. Okay, because you will not find theta, phi, and psi using the relation which I have discussed, or I will deduce it in the next class. Okay, in terms of rate and function. So that's the biggest limitation. Okay, so I think whole video is also saying, telling you what Gimbal Lock means physically in computer game. I think you have understood. Extremely simple concept, Euler angle representation, orientation. Uh, Very useful, but it has problem of Gimbal Lock. And how to come out from the problem, we are going to discuss in the next class. You'll have to listen to the next lecture. Thank you. Have a nice day. Stay safe. Bye bye.